Welcome back to the Python programming series. In our last module, we tackled file handling, learning exactly how Python reads and writes data to files just like real-world applications do. But let's be honest, in real programming, things rarely go perfectly smoothly. Files go missing, users type in the wrong data, and yes, dividing by zero actually happens out in the wild. When that happens, well, normally, Python just crashes. So today, in this explainer, we're jumping right in to transform how you write code by tackling an absolutely critical topic: error handling. We're going to use try, except, and finally to make your program stable, professional, and totally user-friendly.
Okay, let's kick things off with a pretty profound guiding principle. If you look at Tim Peters' famous Zen of Python, which is basically a collection of design principles built right into the language, you'll find this golden rule: errors should never pass silently, unless explicitly silenced. Basically, ignoring problems in your code is never the answer. If a program hits a snag it doesn't understand, it needs to deal with it on purpose, rather than just quietly failing or catastrophically blowing up.
So, what exactly happens under the hood when things go sideways? Well, according to the official Python language reference, when the Python interpreter detects a runtime error, like, say, that missing file we mentioned, it raises what's called an exception. An exception is literally a means of breaking out of the normal flow of your code to tell you, the programmer, that a runtime error has occurred and it needs to be handled right now.
And if you don't handle that exception, it's not pretty. If your code tries to, for example, print 1 divided by 0, and that exception isn't intercepted, the interpreter just completely terminates the program. It stops dead in its tracks and spits out a massive, raw stack traceback, pointing straight to the zero division error. This immediate halt and massive data dump is exactly what we want to avoid when we're building professional apps.
Think about it like a banking application. The contrast here is huge. An unhandled error means the app just crashes immediately. Any unsaved data is completely lost, and raw debug information is exposed right on the screen. But a handled error, that means the application safely catches the failure, gives the user a super friendly message asking them for the correct info, and recovers perfectly, without losing a single byte of data.
Section 1. Try and accept basics. Now that we know the stakes, before we even write a single line of code, we really need to understand the mindset. Python developers love this cultural coding style known by the acronym EAFP. That stands for easier to ask for forgiveness than permission. Basically, instead of writing a ton of complex code to verify that conditions are absolutely perfect before doing something, we just assume valid conditions, try to run the code, and simply catch the exceptions if things go wrong. It's clean, it's fast, and it treats errors as a totally normal, manageable part of life.
The actual syntax to ask for that forgiveness is surprisingly simple. You literally just use a try block and an except block. You drop your risky code right inside the try clause. If it fails, the flow of control immediately jumps out of the try block and straight into the except block to run your fallback code. You can even assign the error to a name so you can deal with it properly. And if no error occurs, the except block is completely ignored like it wasn't even there.
Moving on to Section 2, handling specific exceptions.
Now, catching everything blindly with a generic except clause is kind of a bad habit. We really need to be specific so we can respond with the exact right fix. For instance, the Python reference tells us that dividing by 0 specifically raises a zero division error. We can explicitly catch this exact error by naming it right in our except clause. By doing this, you can tell the user exactly what mistake they made, saying, "Hey, you cannot divide by 0, rather than just throwing a lazy "something went wrong" message.
Or alternatively, what if you ask a user for a number, but they literally type out the letters ABC? The type is valid for text input, but the value is completely useless for math. That triggers a value error. You can actually set up a totally separate except block just for that specific scenario to give a highly targeted, friendly message asking them to please use digits. This kind of precision makes your applications incredibly resilient.
Section 3. Else and finally blocks. Let's piece this whole flow together, because Python gives us two more awesome tools for control flow: else and finally. It's incredibly logical when you break it down into 4 steps. Step 1, you try the risky code. Step 2, except catches the error if it breaks. Step 3, you can throw in an else block, which runs only if the try block succeeded without any hiccups. And step 4, you use finally, which is guaranteed to run at the very end no matter what happened previously. Think of the finally block as your dedicated cleanup crew. Because it always executes, even if an exception was raised or a return statement was hit earlier, it is the absolute best place to release resources or close open files. It basically guarantees you won't get memory leaks even if the program was on its way to a crash.
Section 4. Building safe programs. Why does mastering this flow matter so much in the real world of professional software development? Well, it goes way beyond just keeping your terminal clear of red text. Proper error handling transforms a fragile little script into a robust application. It stops those jarring crashes, it ensures users can safely recover and get back to a working state, it maintains data integrity by shutting operations down gracefully, and, crucially, it secures your internal architecture.
Which brings us to a massive security point. From a security perspective, and this is actually highlighted by the Kiwan security guidelines for Python developers, there's a night and day difference between debug mode and production mode. Deep debug messages are fantastic when you're building the app on your laptop, but you never ever want to leave debug mode on in production. Why? Because those raw stack trace packs we talked about earlier, they are absolute gold mines for hackers.
There's a core Q1 security rule about this exact thing. Hackers actively exploit in-depth debug error messages to map out your application's vulnerabilities. By turning off debug and utilizing try, except, and finally blocks, you're literally putting up a wall between attackers and your systems. You're hiding all that sensitive internal architecture behind safe, controlled, generic public messages.
All right, wrapping things up with Section 5, Mini Challenge and Recap. We've covered a ton of ground in this explainer today, going from the basic philosophy of why we don't ignore errors, all the way to writing secure, crash-proof code. Let's do a really quick recap. You now know that unhandled errors will crash your programs. You've learned the easier to ask for forgiveness than permission mindset. You know exactly how try and accept prevent those crashes, why it's so much better to catch specific exceptions like zero division error, and how to use else and finally to clean up resources. You are completely equipped to keep your applications running smoothly. So I'm leaving you with a provocative challenge to solidify everything you just learned. Can you build a safe age checking app? Try writing a program that asks a user for their age, converts it to an integer to check if they're eligible to vote, but absolutely refuses to crash even if they type out text words instead of numbers. How will you structure your accept block to guide them back safely? Think about it, give it a shot, and I'll see you in the next module where we're going to dive into modules and libraries. Keep coding and keep building those safe, stable programs.